Okay. Hey everyone. Today I wanted to bring here the DeepSeek-V3 paper and talk a bit about it. Of course, DeepSeek has been making a lot of waves recently, right? And I just wanted to make an overview of what the paper tells us, a technical in-depth analysis, and even give a broader picture of what DeepSeek is doing and why it's relevant. So yeah, that's exactly in regards to what we'll cover. I wanted to give like a bit of context, what's driving its innovation, right? Some of the restrictions on exportations of GPUs, then go over the paper and actually analyze technically like all the components. The mixture of experts had a bunch of cool innovations and new ideas. They even did really nice things with communication, quantization techniques, and much more. And of course, the training cost that was super low, and we'll discuss a bit. And it really surprised a lot of people. So let's first start off with the basics. What is DeepSeek, right? Visually, you can use it on an interface that looks and feels like an OpenAI copy. Like it seems very similar. The thing is, it's a very big model. We know the parameters. It's open source, so we know that it has 671 billion. Yet it is very efficient because it's only using 37 per feed forward, meaning per token. When you send it a word, it's actually only using 37 for computation instead of the 600. So it's very efficient. And that brings it to be very cheap. So it's through the API that they're currently providing it. It's almost 30x cheaper than GPT-4. And we'll see about performance in terms of quality, if it's comparing or not. But first I wanted to take a step back and just let's look at who is DeepSeek, what is this company, where did they come from? Just very quickly, it was founded very recently, 2023, by a Chinese entrepreneur, Liang Wenfeng is here. Initially, they actually, the mother company, or rather, Highflyer, this hedge fund, did a lot of AI, so they already had a lot of expertise in it, but they applied it to quantitative trading. I also didn't know really what it was. I digged up a bit, and it is like automating trading rules rather than having employees investigate, analyze, and then decide on what to buy or not, or invest, etc. And this hedge fund was the Kickstarter that allowed DeepSeek to really grow and provided it GPUs, investment, whatever it needed. They already have had a lot of expertise with big AI clusters, and they managed to secure 2048 H800 NVIDIA GPUs. For those who are not too familiar, I'll discuss in a little bit the important technical things about these GPUs in specific. Okay, but why are we even here talking about V3? Why is it so relevant? Again, it is competing with the state-of-the-art LLMs like GPT-4 in terms of quality. People are saying that it looks and feels amazing. DeepSeek, it's with llamas like the open source Claude, which was great at coding, right? And now DeepSeek also shows up great at coding. And it's fully open source, which is one of the biggest things, right? Because of these, only Llama is open source. So now we're getting more heavy players that are contributing to the community, to the research. And it's not just with this V3 paper. They have been contributing with multiple papers with a bunch of innovations over the past 1 or 2 years, right? Since they come up. And they have a very specific thing going on for them, which is that they focus a lot on optimizations. So they focused a lot on trying to achieve a GPT-4o level or a Claude 3.5 Sonnet level, but for much cheaper, much more efficient. We'll see why exactly and how they do that in a bit. They also have some new ideas that maybe GPU makers can use for some improvements. But overall, I think it matters because it's challenging the narrative of China is just copying, right? DeepSeek actually innovates. So it's not just a matter of, okay, maybe they trained on GPT-4o's data, right, on its outputs. Maybe they did. But even if they did, it's much more than that. And that's what I wanted to debunk and uncover here today. So let's start with the obvious and the basics. Benchmarks. Benchmarks, as you know, are always biased. Sometimes do not really portray the real world use, but we'll go over them. This was taken from DeepSeek itself. I did do the average over a bunch of benchmarks. So in English, there were like 5. I did the average on it. Of course, this adds a bit of bias because not all of them are equally important, but it gives us an overall view of it. And we can clearly see that DeepSeek-V3 is dominating over the other models. One of the areas that it actually dominates the most is on coding, where we see that Claude 3.5 was very good compared to the others, and everyone talked about this, even from experience, right? From user experience. And now we see DeepSeek coming up maybe even better than it, which is really surprising. And yeah, it's really surprising, and we'll discuss it in a bit. But one of the key reasons here is because DeepSeek-V3 tried to and was fine-tuned on, or later trained on, a bit of data from R1, the reasoning model of DeepSeek, which allowed it to be better at mathematic problems, coding, these more complex problems. And that's one of the reasons. Okay, again, why it matters, cost. 30x cheaper, like I said. If we actually look at it, we can see that per million tokens, it's not even getting to 50 cents. And it really makes a difference. So I tested out a simulation where I assumed 100K input tokens, 10K output tokens, and doing 1,000 calls of this for different models. Okay, and we can see here that GPT-4o is costing $260. OpenAI o1 is costing, Jesus, 1,500. Imagine how much that is. And then on the bottom, we see V3, okay, the direct competitor of 4o, with only $14, and R1, 57. Compare this to these 1,000. Like, of course, it makes a difference. And this will make the AI industry, especially in the US, have to adapt a lot as new players come in and they provide these amazing prices, right? So it will definitely be good for the overall consumers and researchers as well. Again, they are focusing on efficiency, optimization, and they have been doing this not only since V3, also in V2. So here I brought this chart from one of their papers. I think it's from the V2 paper, where they have the number of activated billion parameters. Okay, so this is not the total number. Again, this is this number here, how much it's actually using to compute per word or per token. Okay, and we can see that it's using a lot less parameters, but in terms of performance, so how good it is, it's up here, meaning that it's very efficient, it's very good, while consuming very little. And so yeah, and we can see Mixtral also here, another mixture of experts model, just like DeepSeek, and we'll go over that also in a bit. The key thing that I wanted to note on is what is making DeepSeek have to optimize so much? What's the driving force for innovation? Well, like I hinted at before, it is having to deal with the US GPU export restrictions. It does have a high impact. So the US has made it so in the past, these H800 NVIDIA chips, they were an adapted version that was available to sell to China, but they had to adapt from the H100s. So these H100s were better, but NVIDIA could not sell them to China because of US export restrictions. They had to make a dumbed down version of it to sell to China. What were these dumbed downs or these restrictions exactly on the GPU? They aren't exactly known, but we do know some things. For example, the connectivity speed between GPUs was heavily capped. Okay, so it's at 0.5 speed of what it was. Why is this relevant? Not for the normal consumer, but for huge AI clusters that use multiple GPUs, it really limits scalability, okay? And we'll see that this connectivity speed is something that you'll see me talking about a lot here today, because it is something that the researchers at DeepSeek had to focus on how to improve, how to find engineering ways to go over this, okay? And then, of course, floating point performance, meaning computations are a bit slower. The tensor cores are suspected to also be limited or somehow limited. So we can definitely see how this goes. And an important thing now, even these H800, okay, that DeepSeek used, have since been banned. So no longer can the Chinese companies use them. As of October 2023, they were banned. Luckily for DeepSeek, they got these beforehand. Okay, so we see that the US is definitely hammering down on them and getting more restrictive. So without further ado, now that I've set up all the context, I wanted us to dive into the V3 paper and actually do a technical analysis on it. I just wanted to say that I've also written a really cool blog post on all of this, including the context of DeepSeek and this paper itself, like the technical analysis. So before I dived into it, I just wanted to say this. So if you have any questions or doubts, you can always check that out. And yeah, here's the link. Hope you like it. Okay, let's start off with one of the most exciting things, at least for me, mixture of experts. Okay, I don't know if you've heard about this before. It's a type of architecture for LLMs. I'll go over it overall what it is exactly. So, mixture of experts. Let's look at this image on the left. It's like having a group of LLMs that each specializes in a different domain. Okay, we can think of it as domains. It may not exactly be this, but we can think of it. And then each contribute to that thing when they are an expert. For example, one may be really good at math or physics. Another may be really good at storytelling or handling, I don't know, whatever. And when the time comes that a topic, so the user made a question about math or coding, there is this gating network, okay, or router that we see here on the right, that is responsible to decide, okay, to which expert am I sending this, or to which, in plural, because it may be more than one. And so this router has to learn what each expert is good at, what it's bad at, and this is how it creates different, almost like mini LLMs inside this LLM that specialize in different things. Again, it may not be really divided into topics, like I said, but sometimes it is, sometimes it's not. And I do want to just touch on the fact that actually I've written blog posts about this, and it's, I think, quite good at establishing the basis of the mixture of experts. And if you want to deep dive there, I think it's a good, good starting point. I also go over Mixtral and how they did it. So you can use the QR code here if you want. So let's start with the diagrams. Okay, don't get too scared. This is simplified. This is a simplified version, and I'll explain it. I promise that it's very simple. So again, looking from this image on the back, we have the router, the gating network, and we have each expert. Okay, the router sends to more than one expert. Then the ones that the input was sent to contribute to the answer. Okay, this is what is here. We have this router. We take input. We have this router. The router will assign a value to each expert, let's say between 0 and 1. Okay, so here we have expert 1 in 0.5, 0.3, 0.1, etc. Then the router will, after assigning a value, and this has been through the router being trained, will select the top K. In this case, let's assume that the top K is 2, meaning that at each point we're selecting 2 experts. So now, because it shows expert 1, 0.5, it will send to expert 1, 0.3 on expert 2, it will send to expert 2. Before we advance further, I do want to say that this is a model with 15 billion parameters that we're taking here for this example. And let's say we have 3 experts, each with 5 billion. Okay. So again, we send these inputs both to expert 1 and 2. So expert 1 has a layer, okay, and it will do the computations. These are usually full feed-forward network layers or dense layers. They may vary in size. For example, here the layer 1 is smaller, then you get the layer 2 that is bigger. But you can do whatever. So you get these 2 layers to process on each expert. Then they aggregate the input, okay, and send it to a new router layer. Okay, so this is like a new router that will decide, okay, we've passed one layer of mixture of experts. Let's now go for the next one and decide to whom shall we send. So now imagine it sends to here and there, and then we keep going and we keep going and we keep going. So it's actually like these experts, they are contributing at different steps, at different layers. Different experts are contributing. And the routers are what are responsible for deciding this. So it's not just one single router. There are routers along these layers, okay? And then finally we get to the output. Now, the total activation size, meaning the amount of computation that we had to make is equal to having a model of 10 billion. Why? Because actually at each point, we're not passing by the 3 experts at the time, we're passing by 2 of them because top K is 2. So we get top K, this is times X expert size, then we get the 10 billion. And this is exactly what makes, for example, DeepSeek that efficient. When I showed you in the beginning, okay, let's go here. When I showed you in the beginning that it had 13 billion, 37 billion parameters, it's exactly what I meant. And actually, yeah, I have it here, perfect. So, and actually I have it here just to show you, it's because it has this mixture of experts architecture that it allows it to be so efficient, because you can have huge number of experts, okay? So you have a bunch of potential computational capacity, but you're only using a small portion of it, okay? Also a small note, these dense layers could also be other types of layers. You could have mixture of expert layers inside of this, okay? And then you would have like mixture of experts inside mixture of expert. Just so you have an idea, a layer of mixture of experts here is like the layer 1, the addition, and the router. This is one layer, okay? But these pretty much mimic mini LLMs, each one of these layers, right? But one thing I did want to make, and just for maybe an easy analogy that you can think of mixture of experts, is thinking like if it is different regions in your brain. Okay, it may not make perfect sense. I'm not an expert on brains, but it can help you understand in the sense that some activities that you do, movement, emotions, fear, whatever, they are processed by different parts of your brain. It's not all processing everything at once. So you get neurons activating or not activating. And this is what MOE does. It tries to separate responsibilities and be able to manage huge potential of computing, but selecting when you need it, so it's more efficient. So now let's actually get to the DeepSeek-V3. And sorry for the delays, but I think it was worth it to make things very clear. Some of the optimizations they did, and just before that, just want to say this graph is pretty much what we saw before. So this is the router. You get the input, you get the experts here, so you can have as many as you want. Here we had 3. Then you concatenate the output and you go to the next layer. Okay, so this is like one layer. Optimizations that they do. They try to dynamically detect high-load experts, meaning experts that are used more than others, because the router may be always sending things to them, maybe because the inputs are always of that team. For example, let's imagine there are always math problems, so it's always sending to the same ones. So the GPUs try to make more replicas of those experts so that they are more easily accessible. No one has to wait for anything. Also, each GPU is hosting more expert than it actively uses, meaning, for example, if the model has a top K of, I don't know, 8 or 9, then the GPU is hosting 12, just so it's a bit bigger. We have more redundancy. We don't have to wait. So that's the main thing that they're trying to avoid, having to wait for anything. Okay, so they want more replicas. They prefer that. So they try to reduce communication efforts as much as possible and slowdowns. So another thing they do, which is really cool, and it's a really game changer, is that while other models use a loss function for load balancing, meaning for the router, okay, so usually this router could be like a mini classifier or whatever, or not a classifier, but like a mini neural network with a loss function that learns from the experts, but then it has problems because it can get too biased, always sent to the same experts, and then those experts, those are the only ones training, the other ones don't train. So it's very hard to balance a training when you do this mixture of experts architecture. It's one of the biggest drawbacks. But they actually pioneered a loss-free load balancing strategy, that they call it this, which allows the router to be much simpler, save much more on computation, and allow for more balance, or rather stability. Yeah, I think stability is the perfect word. So this is actually from the V2 paper that they introduced. I'll go over it very fast. It seems scary, but it's really not. What we have here is that, okay, usually we have the experts, right? In this case, we have 4, 0 to 3, and we have the tokens. And for each token, a probability is given by the router, okay? Usually, like I said, it might be a complex router, and it gives a probability for each. Now, what they did is add a bias, okay? What this bias is responsible for is trying to divide the load between the experts. So the bias is like, if I'm always selecting expert 1 because it's a math problem, now the bias will say, okay, I'll put a negative bias on expert 1 because you're always sending there, so you have to send to others. It's a very simple thing, right? It's a very basic approach, but it allows them to try to keep this mean load of experts, meaning that you try to make a mean of the experts always being trained just about the same. And this allows them to use a much simpler mechanism on the other router itself and not have to deal with this complex routers and handling that. Okay, so one very interesting thing. Of the architecture in DeepSeek-V3, only the first 3 layers are FFNs, so feed-forward networks. After that, it's all mixture of experts, okay? So it's all layers like these ones that we saw here, which is really interesting. Also, they use fine-grained experts, something that they had innovated, I think as well in the paper before in V2, but now they even double down on that, which is they try to use a lot of experts. So 256, they say they use, make each expert smaller. Whereas previous approaches usually went for maybe 8, 10 experts and make them big. This one actually goes for a lot of them. And one of the reasons that they are allowed to do this and can pull it off, let's say, is exactly because of these optimizations on the router that allows all of these 256 to train in a balanced way. Otherwise, training would be chaotic and very hard. So they say that they are using a top K of 8, meaning that 8 experts are chosen per token, 8 experts are routed to by the router per token, okay? We made some calculations. This is just an estimation, not an official number, but each expert could be around 4.1 billion parameters. And they actually have something very interesting here, which is the shared experts, okay? And they are used to allow others to specialize, meaning these ones on the left here. So these shared experts, the concept is that these are always active. So while you have the 8 that you route to out of the 256, then you have N experts. Those are always chosen, okay? Independent of the router, those are always chosen. They do this to create some stability, which allows the 256 to still work, okay, and have some sort of stability, and allows them to specialize more the other experts. So these are in blue here. Why? Because it's like having a central brain that is responsible and learns how to do all the main dull tasks, like understand language, be polite, be whatever. And then you can allow each one of the others to specialize. And because they are so small, this allows them to really go into the detail and be like, oh, I'm very good at this specific thing, instead of having to learn all this clutter that everyone is learning. And then you just have a lot of redundancy when it's really not necessary. You're wasting computing power on that. I wanted to go back to this drawing that we saw before and now look at it through the lens of the fine-grained experts. So here we would be like having 256 of these, right? But the top K here being 8. So you choose 8 out of these. And the shared expert would be like always enforcing that expert 3 is chosen. So expert 3 would be like the main brain that is always there, always present. So it gives some stability to the training, okay? So I just wanted to make this image just so that we connected back to where we started from. Okay, now, let's compare with other models and under previous approaches. I already hinted a bit of this, but previous approaches used bigger experts. So for example, Mistral, the one that I cover also in the blog post that I mentioned, has 46 billion parameters and manages to use 12 or 13 per token. This is very good. It's very good. However, they're just using 8 experts, each one being 7 billion. Okay, so it's like simpler to train. At the time, it was very innovative, and it still is. But now we see companies like DeepSeek really pushing MOE to the limit. GPT-4 was rumored, so the original one, not 4.0, was rumored to be 8 experts of 220 billion parameters, according to George Hotz. But then again, this is just rumors, and in the meantime, GPT-4.0 has definitely been shrunken a lot, distillated a lot of knowledge. It's probably also a mixture of experts, smaller experts maybe, not sure. Now, I wanted to touch on communication. Like I said before, DeepSeek has been investing, and they invested a lot on this communication, making it more efficient. And one of the reasons is because mixture of experts requires a lot of communication overhead, okay? It requires all-to-all GPU communication. Think about this. It means that because at any point I can choose any one of these 256 experts, each one of these might be located at a different GPU, and it can be on the other end of the cluster, okay? So I have no idea. I have to be able to communicate. This GPU has to be able to communicate with any of the GPUs that we have available. So it's all-to-all communication. It's a huge overhead and adds a lot of communication stress. So like I said before, they do this dynamic redundancy for experts, where they duplicate high-load experts. So they notice that, okay, this expert is being used a lot, so I'll duplicate it. And they do this dynamically, which is really efficient, okay? But another thing is that they are using the SMs, meaning the streaming multiprocessors for communication on each GPU, and they try to conserve it as much as possible, making communication more efficient. And they managed to use only 20 out of these 132, okay, which is quite good. Looking at how many communication they have to do. However, it's still a lot, okay? And they argue about this. It's one of the things they complain. So they actually then go on to suggest some GPU design improvements for this, because we're seeing more mixture of experts, more need for communication. They argue that new GPU chips should have communication-specific modules, okay? This would avoid using the precious and the very good at computations SMs for communication, which is not so required. And they really are not supposed to be doing that as much. This having a communication-specific model in a GPU has actually been used a lot by NVIDIA in the past, and they refer to some of the architecture that they used and dropped. And now they're suggesting that NVIDIA or other chip makers may go back to it, because it would definitely help them a lot. And their idea is to be able to not use this, any out of these 132 streaming multiprocessors. Another thing they do, and which I think is really amazing and goes to show their dedication, they actually work on the communication protocol. Okay, so they go down to the detail. They present this dual pipe algorithm. Okay, I have a funny image here, but it's pretty much like this. The pipes going on opposite directions, meaning they overlap communication of forward and backward pass. So we're overlapping communication of weights, gradients, attentions, how they change, tokens, etc. Okay, and they also hide most of the communication that's necessary between GPUs within the computation communication. Also, meaning when you send this forward or backward parse information, you're also sending important communication in the middle. They have this image in the paper. Seems a bit hard to understand at first, but we're going to simplify it a bit. Okay, so these are the forward chunks. So regarding forward propagation information, how the tokens are going, what's like their embeddings or whatever. Then you have the backwards, so you could have the gradients or whatever. And they managed to put them together and overlap, and they're sending like things of the backward chunk and things of the forward chunk in the same communication like block. And they managed to do like computation and communication also on the same block. They managed to overlap all of this. And then you have like really efficient. So when a GPU, okay, so let me simplify this. When a GPU is sending a message to another GPU, Imagine it thinks, okay, I have to send a message because I have to send the computation there that I just computed. Instead of sending that, and then it has computation from another layer of backprop that, it ends up being to the same GPU. Instead of doing those two in separate, they bind them together. And they're like, okay, let me send all of it together. So I'm sending information of a forward propagation of layer 3, a back propagation of layer 4, and whatever in the same communication package. So I won't go into more detail, but it's really innovative and goes to show that they really go to the detail if they have to in order to improve efficiency because of the limitations that they deal with the H800 GPUs. Again, just to hammer that down on this again, takes away from the idea that they just got lucky and copied GPT-4 data. All of these innovations really go to show and actually give me a bit of confidence that they are here to play and they are here to innovate and they are not just here to copy. And let's see what other players do. Okay. Now I wanted to go into one of their also biggest innovations and that I'm very excited about because I've been very into the quantization topic for a while now. And I really wanted to explain this one because it's very cool. Okay. And if you're not aware of what quantization is, I actually wrote a blog post on this a while back that you can check here. I really recommend it because it goes from the bottom up of what quantization is. And it goes more over quantization after training, meaning for inference to lower costs. Here we're going to talk on quantization during the training process, but you can get the key concepts there, so I still recommend it. Anyway, I'm going to give like a TLDR, a very simple one. Quantization is the process of reducing the precision of numbers that represent the LLM to make it smaller. So instead of having, let's think, 10,000 numbers, each one with 5 decimal cases, so like 1.535567, you reduce that, okay, and you make that 1.52. How do you reduce that? Now that's a science, and that's a science of quantization. You don't just truncate or make like a rounding. No, you have to try to make it in a way that avoids outliers being completely messed up or messing the standards up. So it's an interesting science, but if you want the basics, I'd recommend going over this blog post. And I have this image here just to show how much you can actually gain from quantization. So when you pass from floating point 16 to int 4, you really reduce the precision of the weights, and you manage to reduce a lot the space that the LLM takes. Of course, this may have an impact in the quality of the LLM, and this is what you're balancing, right? So you get a cheaper LLM and faster, but you may be losing quality. And often people have seen that going for these 4 to 8, int 8 is like a good point. Int 4, you start losing a lot of quality sometimes. But now let's talk about quantization during the training process, which they did. And it's a very hard thing to do because it adds a lot of instability, because you really need the precision of the weights, the precision of the numbers to be accurate in your back props, forward props, etc. And they do this very smartly. But the way that they did it, they managed to 2x the computational speed, okay? So they also reduce memory consumption. Again, going for floating point 8 is very unstable for outliers. So they developed this technique, fine-grained quantization. What is it exactly? So this is a scary image, but before I get there, let me just explain it like this. When you quantize, you're trying to understand the distribution and then like put everything in smaller numbers, but in a way that makes sense to the distribution. If you only look at the whole distribution, you're going to make a lot of mistakes on some of them. So they do this in smaller, they call it tiles, smaller batches where they quantize here, they quantize there, they quantize there. And this way they get more accuracy with their quantization and they get more stability to outliers. Okay, this is like the overall idea, it's not exactly accurate. I greatly simplified it just for it to be easier. Let's look at it a bit now. So like I was saying, instead of applying one big scaling factor to an entire tensor, right? So a bunch of numbers, they applied smaller localized factors to make each one with less errors. Also, because they are quantizing during training, they have to do quantization and then dequantization, okay? Because sometimes they have to work on higher precision for backprops and whatever. And we can see here, for example, the input starts at 16, BF16, goes to FP8, okay? Then it has to go back to BF16. Here it goes to FP8. The weight gradient, because it's a gradient, it's in 32, right? Then it goes 16, then it goes 32. So again and again, you're seeing like these numbers change. If we want, like just to make this simpler, just think of like you're compressing data when you quantize and then you have to decompress, but it's costly to do this. And it's what they're saying, and sometimes inaccurate, okay? Because to get high precision, it's costly. That's the thing. So they also make some recommendations here regarding GPUs for NVIDIA or for any other chip maker. So they complain, it's, okay, not complaining, but rather they complain and suggest that these GPUs, they only support per tensor quantization, meaning that you have to scale the whole tensor with one big scaling factor instead of having these localized scale factors. So they don't natively support the fine-grained quantization that they want. So they're complaining about that. And then they suggest that the tensor cores could use this. Okay, we won't go into specific over what this is, but the higher floating point 8 gem accumulation precision in tensor cores to be able to dequantize. So let's think of it as decompress. Okay, the number that we shorten now, we learn how to make it bigger again. We get the bigger number more efficiently and more precisely, more importantly. Okay, because they argue that at least 34-bit precision is required instead of 32. Also, they said these current chips don't have, and they would like to have support for online quantization, meaning that these chips would quickly do this in a single operation instead of them having to engineer around this. Okay, this is pretty much what they're saying here. In the paper, they go into more details about this if you want. That's just to get the main idea that they're actually even complaining like, I want to do this. The GPU doesn't have it. Damn it, I'm going to engineer over it. But this will add overhead or whatever. I really hope that future GPUs would have this. That's pretty much what they're saying. Then they innovate on another thing, self-attention layer, something that has been innovated a lot. Many techniques have shown up over the years, right? It started off with a transformer paper. Now we have multi-head latent attention. Don't know if you're familiar with the previous one, so I'll just go over it very slightly. I'm assuming that you are familiar with a transformer. If you're not, I don't think we have a video on it, but there are a bunch online. But a transformer block, so we can look at one of these. It has a tension layer, okay, and then it has the feed-forward layer usually, where here we're using mixture of expert layers because that's the architecture. Okay, this is expected, and this is what they explain in the paper. And as for attention, instead of using normal attention or multi-head attention, they're using multi-head latent attention. And just to make it clear, it's exactly the same architecture as V2 in terms of these blocks here. They just scaled it up a lot. So, previous attention techniques. Like I said, we have the multi-head latent attention that they're using. Previously, we had multi-head, which you have the values, you have the keys, and you have a query per one. Okay. Then you have the grouped query, which then they also used. Wait, was it in V2? Okay, maybe I'm not sure, but I think they also used, which tried to reduce the number of keys and values necessary. Why is this important? Because it's the number of keys and values necessary that really increase the computation of these attention layers, and it's really one of the heaviest parts of the computation process that the GPUs have to do the most heavy lifting. So being able to reduce the amount of keys and values necessary is very important. You also have multi-query, where you really reduce them a lot, but they noticed that it reduced too much, and then you lost a lot of information too, so it was not ideal. So in the process, they came up with a new technique. This is exactly what I showed you before, the first three, okay? And then on the right, we have the new one. Just to be clear, cached during inference, this means that the values and keys are cached during inference, means that they're costly computational wise. That's what I was explaining before. What they do here is that between the keys and values, they make projection, okay? A compressed, latent way of explaining those keys and values together, okay? And if you're not really familiar with the concept of latent space and whatever, I'll give a small like tip on it, or a small scheme that may explain it better. So again, what it does is it tries to compress the attention input, key value pairs, into low dimensional vectors, okay, simpler ways of explaining it, okay, and it uses this low rank joint compression, doesn't matter, but it reduces the key value cache. Later on, they have to calculate it back, right? So pick up this attention, like we said again, like with the quantization, decompress it. And this image here I actually really like. It's regarding, so we're taking images as input, but it's very simple to explain. So we pretty much use an input image, and you compress it into like more features. So this depth, more features, but more compressed data, and you're able to represent it in this latent space, which can then be understood by the same machine, or the same machine as a whole, right, to reconstruct it. And this is pretty much the architecture that's used in super resolution. So if, for example, you want to improve the resolution of an image or video or whatever, I actually happen to work a lot on this and on these type of models. And it's really interesting seeing how the different layers at the latent space representation work and what they focus their attention on. But this is I was digressing, this is the core idea. Great. Now, let's get into what everyone is excited about, or what really shocked the world, I guess, or at least the industry, the AI industry, which was the training cost. DeepSeek had one of the lowest training costs for this kind of offline. It really shocked everyone. Okay, so and we'll go over what exactly they mean by training cost, but they state that the training time cost would be equal to 5.6 million. This is a very low number, okay? But let's look exactly at what this means. This means that the training costs, if you were to assume that you would rent out these H800, which they didn't, they bought them, okay? But if you were to use an online provider, it's not AWS, they specify which one they use there. If you were to use them, they would be $2 an hour for a normal person to use. If you calculated how much they cost for pre-training, context extension, post-training, in which it trained on the R1 outputs as well, would be around 5.6 million, okay? It's an amazing improvement, like even if you look at it from just training time cost. GPT-4, this is a total cost that Sam Altman said at the time was over 100 million. GPT-4o, we don't know. It's probably a lot cheaper. It's still a lot higher than 5.6, I would say. GPT-3 in 2020 was 4.5. So now, think about it. We're doing a model like GPT-3, right? For almost the same price, but now we're using like a 600 billion model parameter, amazing model. We're advancing really fast. I think that's a good take. Oh, and then, okay, this is cool. So this is an estimate that we did of how much it cost maybe to train the Llama 3.1, the 405 billion one. So Meta didn't release these numbers, but they released the training time and the GPUs that they used. So we went to a GPU provider, cloud provider GPUs, and tried to estimate. The cost should be around these numbers, which is very high. Again, Meta bought those GPUs, so it's very different, right? Because when you buy them, it's hard to evaluate exactly how much you're spending because you get to keep them. So yeah, I just wanted to really punch again on this. This cost is for the GPU time for the base model alone. So it's not accounting for RLHF, if it had any. So humans giving feedback, ablation studies that they did, and we know they did. So testing out different versions of the model where they remove certain components and seeing how it affects performance to prove that those components were actually relevant and not just didn't break things and they thought it might be working. Good. Also other runs that they might have done, experiments, smaller runs, data generation from the R1 to train on it, researcher salaries, right? I mean, yeah, people don't work for free. But so bottom line, you could not use 5.6 million you could not take like a huge loan or whatever, or sell whatever you have and train them all like this. But it's maybe a good comparison metric. And we see it as an emerging metric. I think it might be here to stay for the better or for the worse, because you could agree that it's not so accurate. Okay, but it's a good metric. It gives us an idea of like how much it would cost to train this, maybe. Okay. Some keynotes that I want to give. People have been criticizing the V3 model on longer context answers, okay, and this is not really shown on those benchmarks, but more through community experience. So it often becomes repetitive. In storytelling, people have said it's quite awful and underperforms a lot compared to GPT-4o. But overall, and there hasn't been really any research comparing these models at different lengths, so it would be required. But I do want to say that overall, the community reception, and this is the make or break, right, always, which is you can go and say, I have these amazing benchmarks, and it's like it goes over everyone else. It's better than every other model. It cost me only this much. But it's when it gets to the community and people actually get to use it that they start seeing whether it's good or not. And overall, at least from my anecdotal experience, it has been pretty positive, and people have said that the reactions have been pretty positive to DeepSeek being very good and sometimes even better, or sometimes better than GPT-4o, Claude, etc. DeepSeek doing great open source, right? For 2 years now. Let's hope they keep it this way, because it really helps the whole AI community and researchers. They're being the kings right now, right? Reigning over last month and the latest announcements. Even China, right, is taking, of course, major attention on this. They invited Liang, the CEO, to share his opinions on a certain Chinese government policy. It highlights Beijing recognizing DeepSeek. But let's hope they keep it open source. Let's hope this means that other players can enter the market in an easier fashion. Because now imagine if Mistral, maybe a company with not so many resources, could now take some learnings from this, improve on it, make a new model, make a new paper, a really cool one that we could analyze. Others could learn from it. Like, I think it's really good. Let's hope it keeps going this way. And then, of course, there's a question, what's next, politically or whatever, in terms of negotiations. It will be definitely a battle between these two fields, right? The US will keep imposing restrictions. China will try to gain more control over the GPU market. We can see it as the new oil or whatever. And if we have companies like this, like DeepSeek, being able to even provide such good, not sure if it's good, right? But such fine feedback or like precise feedback on the GPUs and what they need and what they think should be the new industry standards. China will probably really value this and try to use it for its advantage. So I don't know. It will be interesting. But overall, I want to I really hope that you learned something from here. And if you have any questions, any whatsoever, feel free to leave a comment, message me, send me an email, whatever. We'll have links below of the blog posts, the paper, etc. I hope it was useful. I know it was a lot to cover, right? We covered a lot. I'm sure. Okay, so just one more thing that I wanted to call our attention to is that there are more players coming in from the Chinese market in the AI field. For example, there's this company, Moonshot AI, It's quite recent. It was founded in 2023, and it has had like a huge investment from big players like Alibaba and Tencent, raising its evaluation to 3.3 billion. Of course, now there's this hype around the AI startup companies, so we don't know exactly how it's going to fare. But they do have like this interface that you can use with their models. For example, they have their reasoning model, Kimi-K 1.5, and they also have like a smaller model, but this one is their most powerful and they're pushing more forward. And they are planning to, or it's reported that they're planning to enter the US market. So I think that we'll hear a lot more from them soon. They have released like this paper where they go over some of the technical things of Kimi 1.5. I must say the model is not open source, so we're not as aware of everything as with DeepSeek, so we cannot test it as easily. The report or the paper, while it does give a lot of information, it doesn't go in depth into the architecture nor nothing like that. So it's really a lot more obscure, all the details and how it actually fares. They do present some results here on benchmarks where they say that, okay, so Kimi-K 1.5 on long chain of thought examples, right? How does it fare? They say it fares, sometimes even better than O1 or etc. Now, I've heard some people say that from experience and from use, it doesn't actually feel smarter than O1, especially on complex problems. So maybe it's a benchmark problem. We never know how these benchmarks can be not manipulated, but you can really cater towards them and not have the same results in the real world. But then on, but then on short chain of thought, they actually show a huge improvement over other models, especially comparing to smaller models like OpenAI's 4.0 or Claude's 3.5 Sonnet. And here, people have been saying that this model is quite good. Plus, it's quite fast, especially when compared to DeepSeek's R1 or OpenAI's O1. It is quite fast. So I'm not going to go more in depth into this, but it's just to give off the idea that there are indeed more players. And let's see what happens. Then I think it will be interesting. Yeah, I'm sure that we covered something useful. At least I hope so. So thanks a lot, everyone. And goodbye.